Thank you. I hope you can all see my screen. I'd like to begin by acknowledging the Whadjuk people of Noongar Nation, who are the traditional owners of the land on which I work and live. So I'm just going to give you a bit of background about what this is. When we build geological models, we start by interpolating geological boundaries. So if we're modeling the subsurface, these boundaries are usually interpreted from the logging of geology from drill hole samples. Nowadays, we're increasingly relying on using measured numerical data such as chemical, mineralogical, or physical properties to provide more consistent information than what we can get from the traditional visual geological logging. So once we have identified the boundaries in the drill holes, then we can correlate from one hole to the next. And this is the way we build our geology model up. To correlate our boundaries, we need to also know what rock types lie on either side of the boundary. So if you look in this example above, to correlate that boundary between the dark green and the dark blue, we need to know it's the same rock on either side. So how do we go about doing this? Well, when we've got numerical data, if we import it into something like Leapfrog, it just interpolates the data and we get a 3D contour model. Sometimes we call this a blob model. And this doesn't actually identify geological surfaces. These are just visualization tools. It helps you see what the distribution of the data is in 3D. So how do we still get the geological surfaces? So if we've got, some numerical data that maybe we got from portable XRF or some sort of XRF scanning or spectral scanning, we end up with this non-subjective numerical data, which is great, but we don't actually have any sort of geological interpretation. What we really want is something where we've actually got intervals which have categorical labels that have geological meaning. And we also need sharp geological boundaries before we can build our geology model. And these sharp geological boundaries could be something like an intrusive boundary, sedimentary boundaries, boundary between lava flows, etc. Now, the problem with finding boundaries is that it's a scale-dependent problem. So if you have a look here, I've got some data. This is from the Mineral Systems Drilling Program, which is from the Gawler Craton in South Australia. I've just got one variable plotted down hole on the left, and you can see the geology log next to it. It's a series of metamorphic gneisses with some silt and gravel at the top. And we particularly chose this variable, which is a log ratio, to pick out the skarn. And you can see that skarn is very high in yttrium over titanium. And it's not a simple change. There's quite a lot of variation near the top and the bottom of the skarn where we're transiting into the skarn. So if we were looking for boundaries at a fine scale or a coarse scale, and you can see those two, what I call lithogeochemistry pseudologs, so these just come from that one chemical element, you can find the boundaries using automated boundary detection algorithms, but it depends on what scale you want. So if you wanted a lot of fine scale detail to see all the small scale variation around the skarn, you might choose the fine scale on the left. Or if you were building a more coarse geology model, you might choose the one on the right. So what do we do? Well, then we need to be able to extract boundaries at any scale. And this diagram here, it's called a scale space plot, and it's extracted using a method called the continuous wavelet transform. And what we can basically do is we can find every boundary, locate what depth it is, and we also work out what scale that boundary is. So if you have a look at the horizontal lines in that diagram, they're the boundaries. Okay, and the extent to which they extend from the left to the right along the x-axis is how strong the boundary is. Now, strength of the boundary is related to both its apparent thickness in the drill hole and also the amount of change at that boundary. So you can see areas which have a really large change have very strong boundaries. They extend a long way from the left to right. And the weaker boundaries, the very small ripples, are just very short boundaries, quite hard to see in that dark blue. The colors there just represent the mean value. So where the mean value within that domain is higher, it's more red, and where it's lower, it's a darker blue. So it's just the jet color range. And we can use these boundaries to divide it up into domains of multiple scales. So if you're a splitter, you'd look on the left-hand side of that diagram, and you can see it's split up into very small units. And if you're a lumper, you move progressively to the right. Okay, and you start grouping the different units together. And you can see those two logs I showed you before, those what I call pseudo logs, which I extracted at a scale of 8 and 20. So that's 8 and 20 on the x-axis. So I'm choosing different relative values of scales. And so from this diagram is very, very powerful. It allows us to select any scale that we want of geological boundary. And then it's just a matter of applying some sort of classification. Typically, when we're applying classification, we're dealing with multiple variables. So here's an example. This is Y-line logging from some public data from a petroleum well, and you can see that there's 6 variables there. And the black lines on those plots represent the boundaries, and the length of the black line is the strength of the boundary. So you can see we can find the boundaries in all the variables, and then we just combine all these boundaries together into a single plot and do the same as what we did before. So you can see here, we've applied a classification. This is just a very simple agglomerative clustering algorithm we've applied, but you can see now it's very nice. You can see how the very small, when we classify every single sample, which is that middle plot, if we classify every single sample, this is very, very fine scale. And if we want to upscale it, then we go to the depth scale plot, and we can see how when we go from left to right, we can progressively upscale. And then we have the ability now to choose whatever scale we want to log at. Okay, and then we, for all our drill holes, we can extract them at exactly the same scale into a CSV file, and then we import it into your 3D modeling software. Okay, so to bring this to you, because this is all written in Python, and to make it easy for people to use, we developed a web app. Okay, the nice thing about having a web app is that it will run on any operating system. You just need a browser. We usually run it in the Chrome browser. It seems to run best in that, but you can experiment with other browsers and see how you go. Okay, the web app is free, but it does have a file size limitation. If you want to access it, just go to our research website, and the address is up there. If you forget the address, if you just Google research CSIRO Data Mosaic, it should bring you to the right link. Okay, so in this, there's all sorts of information in there. You've got the link to the web app where you just log in, and you can start a new login, or you can use your Google login, or whatever option there is there. There's also some video tutorials to get you started. So if you just, they're on YouTube, but that provides the links to those. So it will just walk you through the initial steps to get going. There's 3 there. One is on importing your data. One is on doing univariate analysis, and one on doing multivariate analysis. And we also have a number of different published papers if you want to read those. There's both the theory behind how we developed the what we call the wavelet tessellation. So it's basically 2 parts. The wavelet refers to the continuous wavelet transform, which is the method we use to find the boundaries at all scales. And the tessellation is that rectangularized plot which takes the results of the wavelet transform and turns it into something that looks more like a geological log. If you want more information, you can either email me directly, or there's a general Data Mosaic email there as well, which is very easy to remember. Yeah, I think that's all from me.
Thanks, June. Fabulous. I know that we have one question here in the Q&A. Many thanks, June, from Megan James. Can you use samples of variable interval lengths, both downhole and across variables?
Yeah, so the continuous wavelet transform requires your data to be regularly sampled. So if it's not regularly sampled, what the program will do is it will find your median interval length, and it will resample all your data. So it does a linear interpolation and resamples the data. Now, if you've only got a little bit of irregularity in your data, this is fine. You won't have any problem. But if your data is really irregular or very widely spaced, then that probably won't work so well.